What's going on, everybody? It's Mr. Gustin back in the physics classroom, and today we're going to do the tracking the force activity and then discuss it, okay? So if you weren't here, I'm going to show you the tracking the force activity, and then we'll break down kind of what all this information means for us. So what do we have? We've got this air track, which is kind of like a long air hockey table. It's made of metal, but there are a bunch of holes in it, and when I turn on my power source over here, it's going to push air through those holes. Those holes are pointed kind of perpendicular to the surface, so when I'm laying this track flat, that air is going to push straight up against my cart, which is on the track. So right now you can see cart is on the track, but it's rubbing a lot. There's a lot of friction there, so the cart doesn't move very much. So we'll walk through the 5 different scenarios and kind of track the force and track the motion as we go through. So let's fire it up. I'm going to turn on the power source. You can hear the air coming through. It already starts to move. You can see it right now. Maybe it's not perfectly level, but right now it's moving. So we're going to go into part 1. Part 1 says, let's go ahead and give the cart a push. Let's give the cart a push. So I'm going to take my finger on the cart and give it a gentle push. And I'm asked to track the motion while my finger is in contact with the cart. So the cart starts at rest. It's not moving when it's touching my finger, but as I push it, I see the cart speeds up. The cart speeds up while my finger is applying a constant force to it. The next scenario, part 2 on here, is already, let's track the force or the motion after I've pushed it. So now that I have pushed it, what happens to the motion before it collides with the back side of my track? So I've pushed it, and as I look at it, if I track it pretty closely, that cart is moving at a constant speed. It's actually bounced back, and you can see right now, it's also still moving at a constant speed. Not speeding up, not slowing down, constant speed after I've made contact. Okay? Part 3 says turn the air track off. So let's go ahead and turn the air track off. It's getting noisy anyway. I've turned the air track off, and then it says push the cart on the track and describe its motion. So I want to describe the motion after I've pushed it. So it's left my hand is now sliding on the air track with no air moving through it. Let's track that motion. So ready? Let's give it a push. And it doesn't really go anywhere. I push it, and after I push it, it comes to a pretty abrupt stop. I can actually hear the friction force being generated, that friction force turning into thermal or sound. I can kind of hear it as I push it, like, oh, it comes to a stop. So part 3, the motion is after I push it, it slides to a stop pretty quickly. All right? Part 4 and 5 are a little bit different here. Part 4 and 5 say, let's elevate one side of the track. Let's go ahead and take some physics books and let's elevate one side of the track. So I'm going to do that. I'm going to put my track like this and elevate one side. And then it wants me to place my cart on the higher end. So my cart is going to start over there. I'm going to turn the air track back on, and I'm going to drop it just to see how it moves down the ramp. I'm not going to push it. I'm simply going to let it go. And so when I let it go, it's not moving at a constant speed. It starts at rest, it accelerates, and then it continues to increase its speed as it moves down the ramp. The last scenario we have here is to go ahead and leave it on, but now try to push it up the ramp. So I'm going to start it at the bottom, apply a force on it to push it up the ramp. After I've pushed it, we'll discuss the motion. So not while I'm pushing it, but after I've pushed it. So there's the push. And before it can reach the top, it stops and comes back down. So I push it, it stops and comes back down. So I guess as it goes up the ramp, it is slowing down the whole time until it reaches a point, stops, and then it comes back down and speeds up. So these are my 5 scenarios. Let's go to the front whiteboard and kind of, like the lab says, or the activity says, let's track those forces. Let's draw some force diagrams for those scenarios and discuss what's happening. So in scenario 1, we had a cart on the track, and on that cart, it was on Earth. So we said, hey, there was a force of gravity. I'm going to label that FG on the cart. There was also the track, the air pushing through the cart, or pushing through the track on the cart, was present as well. So we had 2 forces, gravity pulling straight down. Gravity will always pull straight down on the planet Earth. And then the air force pushing back up. And what we saw was that the cart was not really moving up or down, it was moving left to right. So these forces must have been balanced. There must have been no total force on the object up and down since it wasn't accelerating up or down. So we go ahead and put those geometry tick marks on those two vectors saying, hey, these forces, they were balanced forces in the vertical direction. But there was also a force in this direction. This was a force applied by my push. And that force was unbalanced. There was an unbalanced force in the direction of motion. Because there was an unbalanced force in the direction of motion, we saw that this object accelerated. Okay, which way was it moving? It was moving this way. This was the direction of motion, and that's the direction of the unbalanced force. They were both acting in the same direction. We saw an acceleration, and what we actually saw with our eyes. Back. I don't know what happened. Something stopped recording, but I think we're back. We skipped. Where did we end? We talked about the motion and the force being in the same direction. We said there was an acceleration, and because they were in the same direction, it was also an increase in speed. That's where I ended with part one. Part two, or scenario number two, looked a little different. This time, we were tracking the forces after I pushed it, so my hand is now off of it. No longer am I pushing it. My hand is removed. So now that my hand is off of it, I don't see an F push anymore. The motion is still left to right. Here's the motion. I'm still on the planet Earth, so gravity's there. The air track is still on, so there's F air supporting it. Those are still congruent because there's no acceleration up or down. There are no unbalanced forces. All of these forces are balanced. So I see not an acceleration, I see actually constant velocity. So there is no increase in speed. It should move at a constant velocity, and that's what I saw. So this is kind of making some connections, right? There were no unbalanced forces. Newton's first law says if there are no unbalanced forces, objects will continue moving the way they're moving. This object would continue the way it's moving forever, except there's the end of the track and there's a collision, and so it bounces back, so speeds change. But unbalanced forces means no acceleration. I'm sorry, balanced forces mean no acceleration. Unbalanced forces mean there was an acceleration. Our third example was a little different. Number three, now we turned the air track off. We're still on the planet Earth. We turned the air track off, so there's no more force of air lifting and supporting the bottom of the cart, but the cart's still on the track. There's still a supporting force from underneath the object. So what is that supporting force? That's the track. That's F track. And they're still balanced because there's no acceleration up or down, so those forces are balanced. But one thing that I noticed, it was moving this way, but it came to an abrupt stop. And I even heard it come to an abrupt stop. I heard the force. There was a lot of rubbing between the cart and the track, and that rubbing was this way. It was a force of friction. So that force of friction was acting to pull that cart from moving. What I find interesting here is that there are unbalanced forces. But unbalanced forces before meant something was speeding up. But in this case, the unbalanced forces meant something was slowing down. So I think what we've come to realize is that when the motion and the unbalanced force are in the same direction, like in scenario one, we see an increase in speed. And when the motion and the unbalanced force are in opposite directions, we see a decrease in speed. Now, Are both accelerations? Yeah. Acceleration is just a change in velocity. Was there a change in velocity here? You betcha. Was there a change in velocity here? Uh-huh. It's just the difference between either an increase in speed or a decrease in speed. How was the velocity changing? How the velocity changes depends on the direction of motion or velocity and the direction of the net force. If they're in the same direction, we're seeing a speeding up, and if they're in the opposite direction, we're going to see a slowing down. Those were on our flat surfaces. Then we went ahead and moved this thing on an inclined surface with scenario number 4. Scenario number 4, we had an incline. It was at some angle, we'll call that angle theta, and there was my cart. Now, is my cart still on the planet Earth? Yeah, there's gravity, Fg. Was the track or the air still supporting the cart? You betcha. But because I made an angle with the ramp, those little air holes were actually pointed in a non-vertical direction. They were pointed exactly perpendicular to the surface. So I'm going to go ahead and draw my air force, F air, perpendicular to the surface. No longer are air and gravity pointed in the same direction. No longer do they evenly balance each other out. Now there's a discrepancy between the two. So if I asked you which force is the result of this cart being pulled down the ramp, it wouldn't take you long to say, hey, gravity pulls it down the ramp, but gravity also isn't pulling down the ramp. Gravity's pulling straight down, and there's a surface in the way. We have to remember that gravity forces are vectors, just like displacement and just like velocity, which means they have components. So, does gravity pull this down the ramp? You betcha. But it's not all the gravity. Gravity's acting to pull this cart into the ramp. There's a portion of gravity that pulls that cart into the ramp. And we're going to call that Fg perpendicular, because that force is being pulled into the ramp, perpendicular, exactly opposite those air forces. And we're going to go ahead and know that those forces are congruent. They're equivalent because it's not accelerating perpendicular to my ramp. It's accelerating down my ramp, parallel to my ramp. So there also must be some force, because I saw it accelerate down the ramp. There must be some component of gravity that is parallel to my ramp. That's the force that causes it to speed up down the ramp. So here are my components of gravity. I've got some of it pulling straight into the ramp, being supported by the air force, and some of it pulling the cart down the ramp. This is an example, again, of unbalanced forces. The motion in this case was down the ramp. So it's unbalanced forces. The motion is down the ramp. I see an acceleration. Because they're in the same direction, I'm going to see it speeding up. The same principles apply as in scenario 1. An unbalanced force in the same direction as motion, acceleration, speeding up. For scenario number 5, we're going to talk about the cart after it has left my hand. It's still on the incline. There's my angle theta. It's moving up the ramp. So in this case, the motion is not down the ramp. In this case, the motion is up the ramp. It's after it's left my hands. So there's no push force on it. We're still on the planet Earth. There's my gravity force. The air track is still on, so there's my air force pushing on it. Now again, what we saw was the cart went up the ramp, slowed down, and then went back down the ramp. So if I'm thinking about that, I can think about the forces. Is there a component of gravity still pulling into the ramp, supported by the air force? Yeah, there is some of that cart being pulled into the ramp by the Earth. And we call that Fg perpendicular, because it's perpendicular to the surface, just like the air force is perpendicular, and those two are still congruent because there's no acceleration perpendicular to the surface. What force caused this thing to come to a stop and then speed up? We know it's gravity, but it's just a component of gravity. It's just that part of gravity that acts parallel to the ramp. I'm going to call that FG parallel. So, I've got the object moving up the ramp. I've got a net force or unbalanced force acting down the ramp. These are unbalanced forces. And those unbalanced forces, because the force is acting opposite the motion, I see a slowing down as it moves up. But if you go back and let that video play through, it went up the ramp until it came to a stop. And once that motion flipped, once the cart came to a stop and turned back around, we saw it speed up again because the motion had now changed. It was now going down the ramp, and gravity, which is still pulling down the ramp the whole time, is in the same direction as motion now. So now we see it speeding up. We can actually consider scenario 5 in two different parts: motion up the ramp and motion down the ramp. Okay? These are the 5 different scenarios from the tracking the force activity. These are the 5 different force diagrams, and we've even begun to introduce components of gravity on inclines. It's a complex idea, and it's not one that we have to have mastered right now, but it is one that I want to introduce you to so you understand gravity can pull things down a ramp, even though ramps and motion are at an angle, and we know gravity acts exactly towards the center of our Earth while we're on this planet. Okay? Study this up. Make sure you have this in your notes. And until then, enjoy physics. See ya!